variation of y. Uh, what is the meaning of decomposing the variation of y? You know, the other time we started by trying to characterize relationship between two variables, right? Why am I trying to investigate relationship? Because statistically speaking, if I have information about a particular variable, can I say something about another variable? Okay, now we're going to call explanatory variable X. We're going to call response variable Y. Now, what we want to do today, we believe there is a total variation around Y. How can we break it down into variation that can be explained by the model and the one that cannot be explained by the model? I'm going to say that again. How can we actually decompose variation around the response variable? Because we believe we got 100% variation around the response variable. We want to break it down. So the one the model can explain and the one the model cannot explain. The one the model can explain is called explained variation. The one the model cannot explain is called unexplained variation. Unexplained variation is what we call residual sum of square, RSS. Okay, let's take a look at that. That's what we want to do today. That is going to be the focus. Now, I'm going to start with a very good example. Let's take a look at, we want to study the NASA weight of male kangaroos. Okay, now this is the kangaroo. This is the animal that I'm talking about because I want to talk about the weight of kangaroo. And because of that, I actually took 45, okay, kangaroos. I took a sample of kangaroo, okay, 45 of them, okay, and I measured the weight, okay. Now I'm actually going to call Y to be the NASA weight of kangaroo. Now, if you take a look at the plot that I have here, you know, this is when I have a measure of each of the kangaroo. I measure the NASA weight, just like what I said. Now, I got 45 kangaroos. I'm actually going to have 45 values of NASA weight. Now, if you take a look at that, you know, it actually varies, right? It's going to be variation, right? Okay. Now, like I said, I let my Y to be the NASA weight, okay, in that unit. Then because of the fact there's a variation, okay, in the NASA weight of 45 kangaroos, I'm going to be interested in the center, which is the mean, right? Take a look at that. That's the center, right? What have I done? I try to add all the NASA weight together, divided by the numbers of kangaroo, and that give me 244.16. Okay, the 244.16 is the center, is the average. Does that make sense? And you know what? When I have an average, so which is what is indicated here. Can you see the center, right? Okay. Now, the very first question, the next question I'm going to ask myself is how much total variation exists in Y? Okay. How much? We want to know the total variation in Y. Okay, because we believe the total variation occur around the response variable. Okay. Now, if I want to know that, of course, you know what I'm going to do. I'm actually going to be subtracting the mean from each of the NASA weight, right? How many NASA weight do I have? Don't forget, I got 45, right? Then when I'm doing that, I'm going to be squaring them. Then I'm going to add them up. When I do that, that will give me 40196. Oh my God. The total variation now around the, around Y is actually 40196. You know, right now, I'm not interested in what explained that. I'm not looking at the NASA weight in relation to any other variable. I'm only just focusing on the NASA weight alone, looking at the center and trying to figure out what is the total variation around that. The total variation around that is 40,196. Now, and which is that formula that you see right now, okay, which is yi minus y bar all squared, then sum of that. That's what we use in statistics to figure out total variation. We also call that guy SST, sum of squared total. Okay, you can also call it sum of square, SST, sum of square total. Okay, it represents total variations around the response. Is there any question moving forward? Okay, now you know how we find the total variation around response variable right now. Now the next we want to do, let's say there's a good news. And what is the good news? Maybe my colleague collected the NASA length as well. What did I do? I only work on NASA weight. And somebody else now still collect information from the same animals. Okay, the NASA length. Okay, now as we have the NASA weight of 45 kangaroos, we also have the NASA length of 45 kangaroos, and we're going to, of course, we call the NASA weight Y, we call the NASA length X. Okay, now what we want to do now, we want to examine the relationship between the NASA length and the NASA weight. Okay, so that, in the future, I do not need to collect NASA weight if my colleagues have already collected NASA length. Because if I know the relationship, I will be able to use the information I got about the NASA length to explain the NASA weight. Does that make sense? Now, because of that, you know what we always do, right? If we part of the preliminary investigation is to generate a scalar plot, right? To generate a scalar plot between the response variable and the explanatory variable. So which is what we're doing here, right? Okay, can you take a look at that right now? Okay, now the next thing that we want to talk about, on this particular plot, we can actually indicate the Sarah, the length. You remember the length of the NASA weight was 244. I'm going to take you back so that you can see what I'm talking about. Okay, did you see 244.16, which is the length? Okay, so I'm trying to indicate that guy now so you can actually see. Now, the next thing I want to do is this. The regression model. Now, what I want to do now, I already know the total variation for the NASA weight, but I want to know how much of that variation can be explained by NASA length. Okay, now I need you to take a look at this. What I want to do now, if I know X, if I know NASA length, I want to know something about NASA weight. Let me tell you something. In a stochastic world, if you know something about a particular variable, that variable cannot explain everything about the other. It can only what? Explain something. Does that make sense? And I want to confirm to you in today's lecture that even though relationship exists between two variables, a variable S cannot explain 100% of the variation in the response. That's what I want to show you right now. Okay, now, you know what I want to do now? Based on this, we formulated a model. Of course, you know how we get this out, how you get your beta naught and your beta 1, okay? And the moment you get that, the next is, what is the variation of Y explained by the regression model or by X, okay? We already know the variation in Y. We already know the variation in the NASA weight. how much of that variation can be explained by the module. Yeah, I can say by the module or by the explanatory variable x. Okay, now what is the formula am I going to use? Oh my God, I need you to pay attention now. What I want to compute right now is what I call explained variation. Explained variation. Before I can do explained variation, I need to first have my model. Do you see my model? Okay. So that for every X value in the picture, I will be able to get predicted Y, right? Y cap. Now, what am I doing here? Oh my God. What I'm doing here, I'm subtracting the center of Y from the predicted values. Then I square that. When I subtract the center from the predicted value and I square that and I add that up, that will give me the total explained variation. Okay, when I do that right now, we're actually going to have, oh my God, look at this guy. The explained variation is going to be 31,227.9. But what is the total variation? Let's go back and see total variation for ourselves again. Okay, so I'm going to show you what total variation is. Okay, oh my God, look at that. The total variation was actually 40,000. You see? And you see the way we calculate the total variation, we subtracted the mean of Y from the original observation, Y. But when I'm calculating the explained variation, okay, when I'm calculating the explained variation, I'm actually going to be subtracting the mean from the predicted. And at the end of the day, explained variation gave us 31,229. You can see what we got right now. Okay, now, which means even though relationship exists between Y and S, the S cannot explain everything. Okay, now the next thing that I actually want to do now, that is a formula that we use. Okay, that is the formula that we use. Okay, so which is Y cap minus Y bar, okay, all squared. Okay, you sum that together, and that guy is what we also call that sum of square regression. Sum of square regression. Sum of square regression is the same thing as explained variation. Okay, now when I have this guy right now, what is the next? The next is that means there is a variation in Y that cannot be explained. How do I know? Because the explained variation is less than the total variation. Does that make sense? Now, how do we figure that guy out? Okay, this is the formula. Y minus Y cap. You remember the other time? Residual. What is the error? Original? The original values of the response minus the predicted. When you square it, okay, you add them up. This is what we call unexplained variation. Now, unexplained variation right now, oh my God, the unexplained variation is giving us 8,000. That is unexplained. And you know what? Do you know that if I subtract explained from total, okay, if you subtract 31,227.9 from total variation, of 40,000 something here, okay, that is also going to give you unexplained. Okay, if you subtract that is also going to give you unexplained. Okay, now is this surprising? This is not surprising because I told you from day one, we are trying to use model to depict reality, but model can never give us exact characterization of reality. Now, what have we done? Okay, I'm actually going to show you what we've been able to do. Now, you see, I call that RSS, residual sum of squared. Residual sum of squared is what we call unexplained variation. Okay, a variation your model cannot explain. A variation your explanatory variable S cannot explain. Now, because of that, okay, I'm actually going to have this out. Oh my God. What am I having right now? What I'm having right now is this. You're going to see now. This is the decomposition that I'm talking about. Okay. The decomposition I'm talking about is that this guy equal that plus that, which is what? A total variation in y equal variation in y explained by the model or x and variation in y not explained. Okay, let me tell you this. There's always going to be unexplained variation. Unexplained variation can never be zero. Okay, unexplained variation can never be zero. RSS can never be zero. Does that make sense? You remember in my last class I said situation where RSS equal to zero, that is going to look like a perfect model. We can never have a perfect model in a stochastic environment. Does that make sense? Now I need you to pay attention to the formula right now. Okay, this guy is a total variation around y, and this guy is a variation explained, and this guy is variation unexplained. Then what are we trying to do in statistics? We acknowledge the fact there's going to be unexplained variation, but what we normally want to do is to minimize that. We want to minimize unexplained variation. Okay, now that is the decomposition. I'm going to come right now, take a look at this. It means we're decomposing. Now, SST means sum or square total, which is the total variation. SS reg means sum of square regression, which is the explained variation. RSS means residual sum of square, which is unexplained variation. I'm going to say that again. SST means, sum of square total, and SS reg means sum of square regression, and RSS means residual sum of squared. SST is total variation around the response variable Y, and SS reg is a variation explained by the model or explained by X, while the ROSS is a variation in Y that cannot be explained by the model. Now, I actually want to demonstrate this practically. I want to believe you know this guy, right? That's an orange, right? That's an orange, right? I'm actually seeing Y as this, right? But in orange, what do I need in orange? The liquid content inside, right? Okay, take a look at this guy now. Okay. Oh my God. That is what I need. Where is the other one going to go? It's going to go into a trash. Okay, now what I'm trying to say now, this is a trash, okay, and this is that, okay, and this is the whole thing. Does that make sense? That is the way it is. And we want to make sure whatever that's going to go into a trash is going to be minimized, right? Okay, so that is what we mean, okay? So like I said, SST, total variation in Y, and SS reg, variation of Y explained by the model, okay? Now, RSS, variation of Y unexplained by the model. That is the way it is. This is the decomposition that we talk about. Okay, which means there's always going to be something that will go into a trash. That's what we mean. The same way in statistics, we don't have a perfect model. There's always going to be a place for unexplained variation. We acknowledge that, and that was why we said model is not the same as reality. Okay, and which is going, the RSS now is going to represent a gap, Okay, now that is a formula for that. That is the formula for that, and that is the formula for that. Okay, so you can see the three of them are not the same. Okay, when I was focusing on variation around Y, it is just original Y minus the mean of Y. When I'm focusing on Y, you can see in the first one, there's nothing like X, because that's just if we were focusing on Y. Okay, but when you take a look at the sum of square reg, of course, there's an x, because the y cap, okay, the y cap is your fitted module. Your fitted module involve x, right? Okay, I just wanted to take note of that. Okay, now another thing, the same way we can decompose that, we can also decompose the degree of freedom. You know, I know in the textbook you've come across different degree of freedoms. Okay, what did I tell you the degree of freedom for error? The degree of freedom for error is simple linear regression is n minus 2, right? Now, then what is the degree of freedom if I'm talking about just y? Okay, it's going to be n minus 1. Take a look at this guy now. The degree of freedom, when I'm only focusing on y, if I'm not looking at y in relation to another variable, if I'm only focusing on y, it's going to be n minus 1. You know, you've seen that before. What is the degree of freedom for regression? If I have simple linear regression, how many parameters do we have in a regression? Simple linear, 2, right? That would be 2 minus 1. Degree of freedom is going to be 1. Then what about the one for error? Oh my God. Did you see the one for error? How do we get n minus 2? By doing n minus 1 minus 1. Okay? The same way, if I want to get residual sum of squared, I'm actually going to do sum of squared total minus sum of squared regression. If I know the degree of freedom for total and I know the degree of freedom for regression, I can determine the degree of freedom for error. So which is going to be n minus 1 minus 1. That would be n minus 2. Okay? So what I'm trying to show you here is the same way we can decompose the variation. We can also decompose the degree of freedom. Okay, now the next thing that I want to talk about now, that will now lead us to what we call coefficient of determination. The coefficient of determination in statistics is what we actually denote as R squared. Coefficient of determination is different from coefficient of correlation. Let me tell you the difference. You know, correlation will tell you the measures the degree of positivity or negativity, or we also tell you the strength and the direction of the relationship. That is what correlation is going to tell you. But when I talk about coefficient of determination, the coefficient of determination really want to know how out of what it will assign 100% variation for total, for variation in y, and the coefficient of determination will tell us out of 100% variation in the response, how much of that can the model explain? I'm going to say that again. Out of 100% variation in the response, how much does the model explain? Okay, go ahead. Exactly. Which is going to be the ratio. Thank you so much for that. Which send me a message for extra credit. Which is going to be the ratio of the explain to the total, just like what you said. Okay. And I just walk you through explain right now. You know the total right now, then the ratio of that. But let me tell you this. That is the formula, which you just told me right now. Sum of square reg divided by sum of square total. Okay. And in another way, it can also be that. Do you know why it can also be that? Because um, sum of square reg is the same thing as sum of square total, okay, minus ROSS. I think you know that. Okay, sum of square reg is even as that. So divided by SS total, mathematically speaking, SST divided by SST is 1, then ROSS over SST. So you can actually go that way too. Is there any question? Whether in person or online? Is there any question? Okay, now if that is okay, I'm actually going to move. Now, this is the definition. Okay, the proportion of the variation in y that is explained by the regression model. Okay, and that's actually will tell us the goodness of fit of your model. Okay, R squared, you know, measure the goodness of it. How good is your model? Okay. Now, and how can we find R squared in the summary of a fitted model? If you run the code in R, parts of the output that's gonna be generated is gonna be R squared. I'm gonna show you right now. It's actually this guy. Do you see that guy? That's the R squared. When you run a linear regression model in R, automatically it's going to be displayed as part of the outputs. Okay, right now, you got a R squared of 0.7769. If you really want to interpret that, you're going to multiply by 100. What are we trying to say? 77.69%. When you take a look at this, I'm looking at the relationship between NASA width and NASA length. So what I'm trying to tell the world, the NASA length only explain 77.69% in the NASA width. So which means we got some that can be explained by anything other than NASA length, which is going to come in terms of unexplained variation that we call residual sum of square. So take a look at that guy right now. Okay, so like I said, that is that. You're always going to see that in the body of that. Now, let us come back here. Okay, graphically speaking, decomposing the variation of y on the individual level, like on the individual data point. Okay, and I'm going to use if I have a data set and the center is 3.1, the mean of y is 3.1. So I'm actually going to use some arrow now. Okay, and this is the center and this is the fitted. Okay, you see the solid line is the fitted line, the line of best fit, and the dot, the horizontal dot point is actually the center, right? Okay, now if I want to explain graphically, if you take a look at without for putting if you come back here now, take a look at this guy. Y minus y cap is residual, and that is what is being displayed. If you take a look at that, okay, if you take a look at that, then if you go back to y cap minus that, okay, so that is actually when you consider the model, okay. So, and if you continue to go, so what I'm trying to do here is just to talk about the individual level decomposition. But this is what I'm driving at. Okay. For individual, individual I've not squared and I've not find sum. I'm just talking about for individual, but for all observation is when I squared and I sum. So this is for the individual one. Why this is for all observation? In all when I want to deal with the all observation, I'm actually gonna sum, and before summing, I need to put a square. Okay, I'm putting a square because effect of -3, if I have 0 and the distance from -3 to 0 is the same as the distance from 3 to 0, right? So -3 squared is 9. 3 squared also 9. Okay, now so judging from that, and if you really want to see how, okay, if I have this guy at the individual level, okay, which is what I have here, when I begin to square, I'm going to square both sides. Okay, I square this side, and I also square the whole of this guy, which is what I have in the second one. Then after squaring, apply the law of mathematics. You remember when I have A plus B or squared. You know what that means mathematically? That's going to be A squared, right? Plus B squared, right? Plus 2AB, right? Plus 2AB. Okay. That is exactly what we're using here. Take a look at that. Okay. You know, your A is Y cap minus Y bar. Your B is Y minus Y cap. So that's why you have this guy. Any question? Now, the moment you have that guy now, okay, you continue and you introduce a summation. Now, if you take a look at where we are now, we are introducing summation to the O side after squaring, which is what you have here. Introducing summation now. That's what you have. Now, the next thing you're actually going to have, you're going to see that one time is going to be 0. Okay, mathematically speaking, okay, this guy is going to go to 0. And when that guy go to 0, we're only going to be left with this guy. Okay, which is what we are trying to, what we are aiming at. The first one, if you take a look at this guy, okay, it is total variation, okay, explained and the unexplained. But if I want to show how that guy becomes 0, okay, you know, somebody may want to, okay, how does this guy here, okay, how does this guy become 0? Okay, I'm going to show you right here. I want to show how this guy actually becomes 0. Okay, now this guy is this guy, right? Okay, now 2 is a constant. I bring out 2. When I bring out 2, I'm going to have that guy, right? Because that 2 is a constant, right? Okay, now the next thing is, what is Y cap? The Y cap is the module. Okay, do you see? The Y cap is the module. It's the simple linear regression module. Okay, so you can see minus Y bar and Y minus. So you can see what I actually, what I plug in here is just to know, of course, you've done that before, Y cap equal to that. So if I plug that in here, of course, I'm actually going to have this guy here. Okay, I'm only plugging in the module. Okay, now after plugging in the module, okay, the next thing I actually want to do right now. So what I want to do right now, you know, I'm here now, right? I'm actually here now. Okay, now all what I'm actually going to do, if you take a look at inside here, if you take a look at inside here, okay, I can, you know, I have the beta not cap, this one minus Y bar, right? Okay, now if you take a look at this is for this guy here. Okay, now if I actually no, if I put that, you're actually going to see that if I want to substitute for my beta null cap, okay, from here, okay, I don't forget, I know my beta naught cap is Y bar minus beta 1 cap X bar. Wherever I see beta naught cap, you know, there's a beta naught cap here and there's also beta naught cap here, right? You see beta naught cap, what am I going to put? I'm going to put Y bar minus beta 1 cap X bar. They have that relationship. That's what I plug in. That's what I plug in here. What do you see? You're actually going to see this. You're not going to see beta naught cap anymore because the beta naught cap equal to Y bar minus beta 1 cap X bar. Okay, so that's what I have right now. Okay, so if that is what I have right now, now moving forward, coming here, okay, you actually see here I have Y bar and this. What happened? This cancel that. Do you see that? Y bar cancel negative Y bar. What do I have left? I only have those guys, right? You see this guy? I'm gonna have that one left. That is what I have left there after cancel that one, right? Now let's go to the other side. In the other side, there's nothing that cancel out. I'm still gonna rewrite it, right? I'm still gonna rewrite, like I'm actually rewriting this guy again here, right? Now we are there now, right? Follow that with mine, right? Okay, so this is where we are right now. Okay, now if you take a look at this guy, what is common here? Something is common. You can factorize that. It is beta 1 cap. When you bring it out, okay, you can bring it out here. Can you see? The beta 1 cap is joining 2. Okay, you're going to be left with x minus x bar, right? Okay, now when you have that guy right now, okay, now the same thing here. It's also common here, right? You bring it out, right? So that you have this. So finally here, you're actually having this guy, right? Now, when you are having this guy right now, okay, now the next thing is let us now use this guy, okay? You know, if you take a look at this to multiply that, so finally you're actually going to have this guy here, okay? Because this is outside, this x minus x bar is outside, y minus y bar and the other guy is inside. So that guy multiply that is going to give you that. That guy multiply that is going to be that one squared. That's squared. Do you see that? So we're using this guy now to multiply this guy. You're also using that to multiply that guy. And that gives you that. Now, the moment you have that right now, now you can, this is where we are now, right? Okay. Now, let us use the 2 beta 1 to multiply all through. That's going to give you this. Okay, because the 2 beta 1 multiplied by that guy is going to be that. 2 beta 1 multiplied by beta 1, that would be 2 beta 1 squared. Because of the fact that it's outside. You see that? We brought it outside. So multiply all of that. Now, where we are right now, okay, what is this? What is this guy? That should be SSY. You remember? Like a covariance stuff, right? What about this guy? That should be SSS, right? Look at that. Do you see that? Now, if I now want to, and you know that from the law, what is beta 1 cap? The beta 1 cap is SSY divided by SSS. You know what I want to do? I'm also going to plug in, wherever I see beta 1 cap, I'm going to plug in SSY divided by SSS. Now, shear is going to be this guy. And don't forget, this guy is this guy. Any question? Beta 1 is SSY over that. Can you see that? And that guy is SSY. Now, let's go to this guy here. That would be this guy, right? Because the beta 1 is SSY over that. That's going to be the squared. And what about this guy here? SSS. Okay. Now, let's simplify. Okay. If you simplify, right now, where we are, this is going to multiply that. And that's going to be a squared. Can you see that squared, right? Okay. And here, if you take a look at this, okay, this one squared, if you take a look at this, okay, SSS is going to have a squared and it's going to cancel SSS. There's going to be SSS down and that one. So we're actually going to have this. Are they not the same? The outside, we don't just do what we do. There's a reason why we do what we do. Okay, that's how to show that that particular component is going to be equal to 0. Now, lastly, what is analysis of variance? Analysis of variance is the splitting of the total variation into various components. I'm going to say that again. The splitting of total variation into various components. You split variation around the response to components like explained variation and the unexplained. That's what we call analysis of variance. Does that make sense? So the splitting of, and it's going to come in a for, you remember when you have the formula of, and don't also forget this, when you want to talk about the formula of a variance of sample variance of y, that is this. Please take notes. The sample variance of y is the same thing as total variation over the degree of freedom. Look at the top. Is that not total variation? Divided by its degree of freedom. That is the sample variance of y. Okay? So, which means the top is the sum of square variation, which is SST. Okay? And in ANOVA, that is what we actually talking about. That was actually given by George W. Snedeker. Okay? It's very popular today when we want to conduct F tests. Okay? Now, what does F in F distribution test stand for? Okay? So definitely it was named after Ronald Fisher. Okay? You see that F? Fisher. Okay? Snedeker named it after Ronald Fisher for his pioneering work in the analysis of variance. I want to believe George Snedeker was a student of Ronald Fisher. Okay? So they work together on the analysis of variance. Okay? This is the distribution. We call it F distribution. This is showing F distribution has two different degrees of freedom. And that's what you can see here. But you know where I'm going? This is where I'm actually going. And I need you to pay attention. When you run a regression model, you have this output, right? Okay. We conduct a t-test. We conduct an f-test. Okay. The t-test is for the individual parameter. I told you the other time. Okay. Like, if I want to know, do you see when we make use of those p-value? We conduct a t-test on the individual parameter in a model, but we conduct an f-test using this p-value when you want to look at the overall significance of the model. So we have a t-test, we have an f-test. Now, I need you to pay attention now. What do we use f-test to do? We use f-test to it's a test between intercept model and a full model. What do we mean by intercept model? In intercept model, okay, we don't consider any explanatory variable. Situation where you are comparing nothing, intercept model is like, there's no any explanatory variable in it. You want to compare that with the full model that have an explanatory variable. Now, what is the hypothesis you're going to set up? H naught, you're going to say, oh, intercept model will do the job. Alternative, full model is more adequate. Okay. Now, if I want to conduct this test, I'm actually going to use an f-test. Now, using an f-test, which is synonymous in simple linear regression, this is synonymous testing the significance of slope. In simple linear regression model, the p-value for f-test is going to be the same as the p-value for when you are testing for significance of the slope. They're going to be the same for simple linear regression model. Now, what is the test statistic? The test statistic for F, I'm trying to tell you how they got this guy here. You see 149.7, 149.7. What formula do they use? You don't know. The arrow will just give you that, right? What formula? Now, I want to show you the formula. Please take notes. The formula is this. The formula is this. Sum of square reg divided by 1. Then divided by, why is it divided by 1? That 1 is the degree of freedom for the model, because simple linear, you have two parameters, right? Then RSS, that is residual sum of square divided by n minus 2. Why n minus 2? N minus 2 is the degree of freedom for error. Does that make sense? So the first one, sum of square reg divided by 1, that 1 means the degree of freedom for the model, and n minus 2, the degree of freedom for the error. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . And of course, we actually going to check if I want to find the p-value. There's going to be 2 degrees of freedom. One, the degree of freedom for the module, n minus 2, the degree of freedom for the error. Okay, because I'm going to check for the p-value. Okay, now in the end, I'm going to show you a result. Okay, take a look at this now. When you run this, okay, this guy is what we got when you make use of the formula. Okay, and it's even going to report this to you. Can you see that? Degree of freedom 1 and 43. That 43 is the degree of freedom for error. Okay, and how are you going to get, like for instance, if I wanted to use R to obtain sum of square regression, sum of square total, sum of square error, how are you going to do that? You're going to do ANOVA into your module. Do you see this? ANOVA into MOD. Your MOD is when you do LM. Okay, you know, MOD, your MOD, your MOD equal LM. Okay, whatever your Y is, right? On X, right? Where you have your data, you know that you always put, okay? Now, when you want to get, you know, the ANOVA, you just write ANOVA into mode. Now, let me quickly explain this. Look at this section. What do you see, sum of squared? This guy here, we got it that time, right? That is the sum of square regression. You remember when I was explaining the NASA length, NASA width, the variation, we got 31,2279.9. You can see here, that is the sum of square regression, which is the total explained. What about this one? What about this one here? That is the sum of square residual, unexplained. How am I going to, your arrow will not give you the total variation. Can somebody tell me what are you going to do to get a total variation here? What are you going to do to get a total variation? You add them up. Yeah, you're going to add this and this. That will give you that 40,000 that I showed you initially. Do you see now? So if somebody asks you here to get R squared, what are you going to do? It's just going to be the ratio of the explain to the total multiplied by 100. So this is how to get the ANOVA into MOD is what you're actually going to do to have access to sum of square, you know, sum of square regression, the sum of square residual, and so on and out. Okay, now if you take a look at this guy now, see this divided by 1. You remember that time? We say sum of square reg in the formula for F, right? Sum of square reg divided by 1. And this divided by 43 is the n minus 2. Then after that, whatever you get, you see this guy? That will give you this. What is going to be your F? This F value here is the mean square error for length divided by the mean square error for residual, which is the formula here. Which is the formula here. Can you see that formula? For you to be able to get, your F. Okay? For you to be able to get your F in the table. Okay? Please know the relationship, how they got this guy here. Okay? Know the relationship. Lastly, that is all what I, okay, so, oh, sorry. Okay. Okay, see, which is what I got for you for today. Is there any question, whether in person or online? Is there any question? Go ahead. Oh, S36 formula. Give me 1 second. Let me see if I can. Let me first. So 1 second, I'm gonna share that again. Oh, where's this guy?